Good evening to all. Today I am going to present the title on frequency selective surface. So this is the outline of the presentation: Introduction to frequency selective surface and motivation, classification of frequency selective surface, geometry and objective of the frequency selective surface, and applications of the FSS. So first one, introduction. So in general, in present scenario, there are more primary challenges that need to be addressed in wireless communication system. So the new techniques are implemented mainly for increasing the channel capacity and improving the data rate in the wireless communication system. Here the frequency selective surfaces are introduced. So the main function of the frequency selective surfaces, it is a thin repetitive structure which is mainly used to transmit or reflect or absorb an electromagnetic waves within a selective or within a specified particular frequency ranges. So sometimes the FSS frequency is act as the spatial filters. So it has some unique characteristics mainly for controlling the propagation of electromagnetic waves in a particular frequency band. Here the unit cells are introduced, the smallest identical elements of the FSS array, which contains more number of elements, that is called as unit cell. Here in FSS, the unit cells are periodically arranged in one or two dimensional array that forms an entire FSS structure. So here the FSS is also called as partial filters. So the main function of the filter is it is used to band stop or band pass the electromagnetic waves from source to destination. So this is the main purpose of a frequency selective surface. So in general, the frequency selective surface are utilized in various applications, mainly for passing and band stop the particular frequency. So here, partial filters is subdivided into four classes. So first one, slot patched array. It gives us low pass filter, and slot array geometry. It produces high pass filter, and loop elements array. It produces the band stop filter, and loop slot array elements. It produces the band pass filter. Here the filters are classified into four types, that is low pass filter, band pass filter, high pass, and then band stop filter. So based on the FSS design, here the bands are classified. So filters are classified. So first in figure A, so the response is nothing but low pass filter. So the structure is nothing but solid patch geometry FSS. Here in general the solid patch geometry will always produce the low pass filter, and slot element array geometry which gives the high pass filter. So this is the response of high pass filter. And in C, it acts as the loop element array. So in loop element array, it produces a band stop filter. So in general, the FSS we are using only the band stop and band pass filter. So we are considering only loop elements and loop slot array for the FSS structures. And next one, D represents the band pass filter. So in band pass filter, we are using loop slot array geometry. So this is the loop elements and this is the loop slot array geometry elements. So mostly for in real-time applications, for example, in radome structures and in satellite communications, if we want to reject some bands, some few frequency band at a certain frequency, means we can utilize these two structures in the FSS elements. So the main function of the FSS is mainly used to band stop and band pass the electromagnetic waves from source to destination. Next one, classification of frequency selective surface. Here, the classifications is based on three classifications. So first one, it is based on elementary, and next one based on structure and based on applications. So first one, in elementary, it consists of FSS geometry. So that is the basic element is element type, and we are considering more number of FSS structures are there. And we are, for example, here I mentioned convoluted Mendel shapes and then fractal element. In next slides, I discussed about some few geometry of the FSS based on the array element, and next one based on the structure. So based on the structure, here the frequency FSS is divided into four category. One is single layer structure, multi-layer structure, stacked layer, and then three-dimensional layer. So based on the applications and based on the frequency ranges, we can select the number of layers, that is structure. We can select the structure of the FSS element and based on the applications. So based on the applications, mainly the FSS frequency selective surface, it covers the entire applications like observer FSS, active FSS, and then wearable device FSS, and active skin FSS and optical FSS, and also we can utilize the FSS in textile applications. These are all the some few applications of the frequency selective surface. And next, objective. So the main objective of the frequency selective surface here in frequency selective surface, we are going to improve the fractional bandwidth and then angular stability of the unit cell. So mainly for improving the fractional bandwidth, and we are calculating the angular stability of the FSS element up to maximum degree as 360 degree. So the main function of the FSS, we are calculating the analyzing the performance of the FSS in terms of transmission coefficient, reflection coefficient, and as well as absorption coefficients. So by using the transmission, reflection, and then absorption of the electromagnetic signals from source to destination, here we are calculating the performance characteristics of transmission, reflection, and then absorption coefficients. That is, transmission is nothing but transmission coefficient is nothing but S12, and reflection coefficient is denoted as S11. And finally, we are calculating the absorption coefficient. The absorption coefficient is based on transmission and reflection coefficients. And next, we can able to control the electromagnetic waves, that is polarization control. And next one, under polarization control, we are taking polarization conversion and as well as filtering. So polarization conversion means we are converting linear polarization to the circular polarization or circular to linear polarization. So this is the conversion process we are taking in the polarization type of frequency selective surface. And next one, frequency band. So frequency band in general we covered almost microwave frequency band, that is from L to D band, and entirely it covers the applications of mobile communications, wireless LAN, and then electromagnetic shielding, satellite communications, and then radar. Mostly in the FSS structure, we are utilizing in shielding purpose, and then as well as in satellite communications, and then radar purpose. We are using the frequency selective surface structure in the transmission purpose of the wireless communication systems. Next one, motivation. So motivation, we are covering wideband frequency ranges. So wideband means it refers to the wide range of frequency, and it can allow the efficient transmission from source to destination within a specified frequency ranges. We are in filters, we are using only the band stop and band pass filter. That means we are rejecting some electromagnetic signals in the specified band, and we are passing some electromagnetic signals at the particular frequency. This is the main motivation of the FSS, and mainly we are going to increasing the channel capacity and then enhancing the data rate in the wireless communication system. And polarizers. So polarizers we are using only for the controlling of the propagation of the electromagnetic waves, and we can utilize it for the applications such as electromagnetic shielding and as well as in radar and then radome applications. And FSS, it is mainly to provide the precise control over the electromagnetic waves, and we can improve the performance level of the transmission and reflection coefficients and as well as absorption coefficient, and also we can reduce the interference in the wireless communication system, and we can utilize the FSS in innovative applications in the wireless communication systems. And next one, these are all the frequency band. So in previous slide, I mentioned band up to from L to D. So this is the particular frequency range for the certain band. And here I mentioned the applications of the frequency ranges, particular frequency ranges, and then a band of the frequency ranges. And mainly we are using the X band, that is 8 to 12 gigahertz, that is in radar communication. So almost the microwave frequency band, it covers to entirely band from L to D band, that is from starting from 1 gigahertz to 170 gigahertz. So based on the frequency range and based on the wavelength and based on the applications, we can design the FSS unit cell according to the frequency band and then applications. So before designing the FSS structure, we need to first select the frequency range and then applications. So based on that, we need to design the structure. So based on the structure, there are in previous slide I discussed the classification of the FSS. So based on the structure, we can utilize the single layer structure, multi-layer, and then stacked layer. Next one, these are all the few geometry of the FSS. So that is shapes of the FSS. So first one, here I mentioned dipole FSS, and this is nothing but tripole shapes. And next one, circular loop. We can design the FSS structure in term that is based on the wavelength and then frequency range and then length and width of the FSS elements and circular loop. And this is the square loop structure and then circular patch and then square patch, and this is nothing but Jerusalem cross shape. And next one, tripole with V slots and then hexagonal patch and then hexagonal loop and square spiral and then Jerusalem cross structure. So based on the geometry of the FSS structure, we can transmit the electromagnetic signal from source to destination. So it can transmit or reflect or it can absorb the electromagnetic signals from the entire base station, that is from source to destination. And next one, geometry of the FSS. So these are all the few geometries, that is it is nothing but the convoluted square leaf. So these are all some few fractal elements FSS. So this is slightly difficult to design. So, but the result of the FSS structure, that is convoluted element, is very good. So the bandwidth of the FSS we can improve by using these few structures. We can improve the fractional bandwidth and as well as the angular stability of the FSS, and polarization conversion is also possible in the fractal elements of the FSS structures. So these are all the few fractal element structures in the FSS. And next one, structure of the FSS. In classification, previous slide I discussed. So there are three classifications based on the structure. So first one, single layer structure, multi-layer, and then three-dimensional layer structure. So this is one example of the single layer structure. So this unit cell is nothing but bow tie shape of unit cell. Here we designed the bow tie unit cell structure. So first one we are placing the bottom terminal, and next one substrate we are placing the substrate, and after substrate we are designing the unit cell structure. So this is nothing but single layer structure. And next one, multi-layer structure, it consists of four layers. So first one, bottom layer, and second one we are placing the dielectric substrate, either FR4 and then ROGES. There are so many dielectric substrates. So according to our specifications, that is according to our frequency ranges, we can select the dielectric substrates. And next one, middle layer, and after that top layer is nothing but design of FSS unit cells. And next one, third one, three-dimensional layer, that is 3D layer. So this is the cylindrical, for sample I am showing the cylindrical 3D FSS structure. So based on the frequency ranges and the number of layers, we can design the loop elements also, that is in 3D FSS. So these are all the few examples of the structures. And next one, equivalent circuit model of FSS. So after designing the frequency selective surface, we are going to implement the ECM model of the corresponding FSS structure. So equivalent circuit model is the most important in FSS part. So we are just verifying the equivalent circuit of the corresponding FSS structure by using the tool, that is ADS or AWR. There are so many tools. So in general, I measured in ADS and then AWR tool for the equivalent circuit model. So that is, this is the entire slot element. So the slot element which consists of the gap. So the gap, it produces the capacitive elements, and the patch element will generate the inductive elements. So based on the slot element and then patch element, we are creating the capacitive and inductive elements in the FSS. So based on our design, we are creating the slot and patch element. So in general, plot elements we are always consider only for the gap is nothing but capacitive elements, and then patch element we are creating the n number of inductors. Based on our design, we are plotting the equivalent circuit for the corresponding FSS structure. So this is the basic general step for defining the equivalent circuit model of the FSS. And next one, this is the general steps to design the FSS element. So first defined requirements. So in defined requirements, I already discussed. So that is, we need to choose the frequency band and then application and the type of filters. So type of filter means either based on the slot element and then patch element, either the FSS structure will act as the band stop filters or a band pass filter. So that is the type of filter. So before designing the FSS, frequency selection and then type of filters and then application is very important. And next one, select the element geometry, that is shape of the unit cell. So in previous slide, I mentioned the few geometry of the FSS. So before, after selecting the frequency ranges and then types of filters, next we need to design the shape of the unit cell. Either it may be a circular, some loop or Jerusalem cross and then square loop. So there is few, more geometries based on the element and then based on the layers. So according to our convenient, we can choose the shape of the unit cell. And next one, estimate dimensions. After choosing the shape, we need to fix some length value, height value, wavelength, and then periodicity. So once if we choose the frequency band, afterwards, after choosing the frequency band, first we need to calculate the wavelength and after that periodicity and then length and height of the element. So these are all the main parameters for designing the FSS structure. And next is substrate. So substrate is very important part. So by choosing the substrate, it can produce the more efficiency, that is more bandwidth. So first we need to choose the dielectric constant, that is dielectric substrate. So if dielectric constant maximum, we are using FR4 and then Rogers substrate. In Rogers there are so many permittivity values very different in Rogers. So according to our frequency ranges, we can choose the dielectric constant and then tangent loss, thickness and then conductor type. So conductor mostly we are using copper. And next one, simulation tool. What we are using for this for designing of FSS tool is nothing but CST, Microwave Studio and then ANSYS HFSS. So mostly we are using CST, Microwave Studio software for simulating the FSS structure. And next step, optimize. So these are all the few parameters we are calculating the FSS part, that is resonant frequency and then bandwidth optimization, angular stability and polarization conversion and then selectivity and then losses, that is insertion loss, and then based on the filter type we can utilize for the reflection based on the type of filters. So these are all some few optimized parameters we can analyze in the FSS. And next one, validate for angle. That is nothing but polarization. So for both transverse electric field and then transverse magnetic field, we can calculate the incident angle up to maximum 180 degree or 360 degree. So mostly in FSS, the maximum angle is 0 to 60 degree. We are calculating only for the up to 60 degree. So based on our design only, we are taking the angle of incidence. And next one, fabrication. So after completing this process, after designing the FSS structure, next we are going for fabrication process. So based on the layers, that is single layer, it may be a multi-layer or it may be a stacked layer or three-dimensional layer. Fabrication is utilized for the design FSS structure. And finally, the fabrication prototype can be designed by using the PCB etching and photolithography and then printing. So in printing, there are screen printing and then inkjet printing and then laser etching. So mostly in FSS structure, I used a PCB etching process for the fabrication of the entire FSS prototype. And next one is parameters. So after designing and after prototype, after we are completing the prototype process, we are going to measure the S parameters in anechoic chamber. So maximum we are using, we are calculating the transmission coefficient and then reflection coefficient, that is S21. So transmission coefficient is that is S12 or S21, and reflection coefficient is nothing but S11 or S22. So these are all the two parameters. Finally, we are measuring in the anechoic chamber after fabrication process. And next, we are integrating the entire FSS structure into an antenna based on the applications. We are utilizing the entire FSS system. It may be either random structures, or it may be a random applications, or it may be satellite communication purpose, and also for the shielding purpose we can utilize the entire FSS design. And finally, we are integrating into the antenna type. And next one, applications is, so these are the few applications I mentioned here. How we are fixing the FSS structure in the AMI shielding, and then random structure, and also in satellite communication, that is in wireless communication. So first application here I mentioned random structure. So in random part, this is the FSS prototype. Here we are fixing the FSS element in the random structures. And next one, this is EMI shielding. So for example, here I consider our mobile phone. So first, this is the phone housing, and under PC, under the phone, under the mobile part, we are fixing the antenna array. So antenna array, it is nothing but based on the element structures and based on the frequency ranges, that is we are fixing the antenna array. And then PCB, um, this is the PCB structure we are using for the mobile phones. And then this is the this is the FSS elements. And next one, this is the touch screen. And next one, wearable FSS, and then 5G communication systems, we are using the FSS elements. And 5G, in 5G communication system, that is FSS element is placed in the base station. We are transmitting the from the base station. We are transmitting the electromagnetic signals from source to destination process. That is based on the frequency ranges. We are giving either it may be a band stop filter or it may be a band pass filter. We can fix the FSS element in the wireless communication system at the base station. Thank you.